Hi, everyone. Welcome back to Bufnagle the podcast, where we explore entertaining and enlightening discussions of the adventure of life and all things good. From science and technology to history and philosophy to leadership and success. We hope to give you a better understanding of the world and skills for everyone to pursue their own adventure.
Hey everybody, welcome back to Bufnagle the podcast, where we talk about all things good and the pursuit of the adventure of life. I'm Rafe, and it's going to be a great one today. We're talking about all sorts of things that we're gonna put to rest some questions that have arisen to us over the years, and I'm going to bring in a very special guest to do this. We got Harry here on the line in the studio, and he's going to be assisting me today. Harry, how are you?
Hey, Rafe. I'm doing great. Excited to be here. I'm excited to get learned, as they say. I think our pre-production meeting I already, didn't know a couple things, but I'm
Really?
sure we'll talk through them and learn some more about them.
Yeah, so this is going to be a good one. Just before we get started, I got to thank the listeners. Hey, thanks guys. Thanks for being here. We appreciate you showing up and putting a little skin in the game. Thanks for hitting that subscribe button. If you're new to the podcast, hey, hit that subscribe button. Give us a 5-star review. Get us some pudding and some cookies and stuff like that. We appreciate you coming out to listen to us, and you can always reach us at bufnagle@bufnagle.com. And we're on Twitter and all over the Harry. We are everywhere on the internet. It's just I'm not even going to go into. I mean, I like you list it. We're there. All right. So give us a like or a smiley star or a thumbs up or whatever it is. Harry,
Yeah.
I keep getting these questions, okay? Because I got friends from like I got a lot of good friends here in the U.S., but I got great friends in Canada and from all around the world, and they always ask me this thing. They're like, "Dude, you got to tell me, why is the U.S. so stupid when it comes to the metric system?" And that's the kind of thing they asked me. I remember being like in 4th grade in the 70s, and they were like, "Hey, we're going to the metric system," which means that some of the signs, instead of saying like Cincinnati 60 miles, it would say Cincinnati, I don't know, 98 kilometers, whatever the number was, right? So
Sure.
that's all they did, right? Was do that. And people were like, "How come you don't use the metric system? Everybody's using the metric system." So, I mean, you've seen that, right? In
Sure.
the
Yeah.
army,
And
travels around the
you heard it
world.
all the time. I mean, the Army uses metric, but that's just what they've always done.
Well, they haven't always done that.
Well,
I
since
mean,
I've been
like,
around.
oh, right. So that's the question: is why don't you use the metric system? Because the metric system's awesome. And you know what? I will be the first to say the metric system is awesome. I love the metric system. It is a great thing. If nothing other than just the prefixes on the units make my life wonderful, and they help you. I don't know. If you're into math, the metric system is the place to be. Powers of 10 are really nice. Unit conversions are simple. All right, so the metric system is a set. Okay, I looked this up. Okay, it's not really the metric system anymore, Harry. Did you know this? It's now the System International, and
Sure,
it's
because
really
everything's French.
yeah, it's in French somewhere. So there's some. I'm sure I'm saying it wrong, but there's some accents on some of those words. But it's the SI. These are SI
Mm-hmm.
units, is what they're called. Okay, and there are actually 7 fundamental units. Okay, there's 7 that need to be defined, and everything else follows through dimensional analysis of them.
Yeah, absolutely.
Okay, so
What are they?
so okay, so here they are. Okay, in no particular order, they are length measured by the meter,
Yep.
time in the seconds, quantity, right, which is measured in moles, right? They don't use dozens or baker's dozens or
It's
gross
really hard to
anymore,
measure
right?
population that way, huh?
Yeah, I just count individuals, but if you're counting groups of individuals, you use moles or you use I don't know. A gross is 144, right? If you're
Yep.
chicken eggs, right? Okay. Current is measured in amperes. Temperature is measured in Kelvin. Luminous intensity, that's like how
Mm-hmm.
bright a light is measured in candela. And mass is measured in kilograms. And everything on the planet that you measure, like in sciencey stuff, comes from those 7 units, how you put them together. All
Yeah.
right, so kilogram meters squared per second squared is like newtons or something like that, right?
Kilogram meters per second. Yeah. Because it's force, mass times acceleration.
Yeah, it says force. That's newtons. Yeah. Okay, see, so they all come from those things. Okay, now the SI system is great because it has all these different fun little words to say to make things better. So if you start with just a single thing like a meter, and you have 10 of them, that's called a decameter.
Yep.
Right, and then 100 is a hectometer, and 1,000 of them is a kilometer. All right, or a kilometer, depending on where you're from. And then they stop doing the integer powers of 10, and they just go to every 3. So 10 to the third is kilo, and 10 to the 6th is mega, and then giga, and then tera. Then peta is 10 to the 15th. Exa is 10 to the 18th. Zeta is 10 to the 21st. And yata is 10 to the 24th. Did you know that? Yata?
It sounds like Yahtzee.
Well, and I'm trying to think, what do I know that has, other than like light and like universe things, what do I know that ever needs a power of 10 that big? And the answer is the mass of the Earth is like 10 to the 24th kilograms. So it's like
10 to the 27th grams.
10 to the 27th grams, or 1 yottagram.
How much do you weigh? Well, rounding up or down to the nearest yottagram. Yeah.
Yottagram. So that's yottagrams. Okay, so that's, you can use that. And going the other way, getting smaller, 1 over 10 is deci. Okay, so there are 10 decimeters in a meter. There's 100 centimeters in a meter. There's 1,000 millimeters in a meter. And then it goes to the powers of the threes again. Okay, 10 to the minus 6 is micro. 10 to the minus 9 is nano. Then we've got pico, femto, atto. These sound like the Marx brothers, don't they? Zepto and yocto. 10 to the minus 24th is yocto. So that gives you 48 orders of magnitude, 24 down and 24 up. And you can pretty much cover, if you're doing outside of that, just do yada giga or something. Just put them together and you can get them. Right, and so that should be a pretty easy thing. It's interesting to me because when I looked this up, some of these prefixes are Greek. Okay. Most of the bigger ones are Greek, but the last two, zeta and yada, are Latin. I had no idea. Right, and with the deci ones, there's some other things thrown on, like deci, centi, milli are all Latin. Micro and nano are Greek. Pico is Spanish in its origin.
Okay.
Who knew? Right, and then the Danes have femto and atto, and then zepto and yocto are both Latin. So, we got all these ancient languages in here. Zach would be having a field day, but he's busy doing some other things right now. So
that's all right.
He's okay. So that makes the metric system pretty awesome. Okay, and I think that's kind of cool. But there's a thing, like if you're a computer guy and you have a computer right there in front of you. In fact, you're talking on it right now. So, and you have megabytes on your computer, right?
Sure.
And kilobytes and things. Okay, so a kilobyte, you would think that is 1,000 bytes, right?
More or less, yeah.
Yeah. Well, I would think it would be exactly 1,000 because it feels like it's metric and it's kilo, right? But a kilobyte is actually 2 to the 10th bytes.
1,024.
1,024. So a kilo in binary is 10 to the 24th, and a kilo in metric is just
10 to the third.
Did I said 10 to the 25. I meant 1024.
Right.
All right, and it's 10 to the third in metric land. And then a mega is not mega is 10 to the 6th in metric land, but it's 2 to the 10th squared in computer land.
Mm-hmm.
All right, so it's like 1,000, okay, or it's a kilo, and a kilo mega is a giga, which is 2 to the 10th to the third, and a tera is 2 to the 10th to the fourth. So it kind of lines up, but it kind of deviates. It's deviating a little bit because 2 to the 10th is a little bit.
So what you're really telling me is we shouldn't have rocket scientists be doing our data analysis.
Well, that's certainly a possibility, depending on how well they are trained. But the idea that so you just got to be really careful. 10 to the third is not always, or kilo is not always 10 to the third. Sometimes it's 2 to the 10th.
Sure.
So you know what? What do they say? Caveat emptor, computer man beware. Is that what that means? Something like that?
Couldn't tell you.
No, it's buyer beware, right? Caveat emptor.
Okay.
It's Latin.
Latin.
Okay.
Yeah.
Okay. So that's the basis of the metric system. But what I always hear is that the metric system is great because it's based like on real stuff. Like the imperial system, like inches are like that's like the king's thumb, and that's stupid because it's just
Yeah, and they got the exact meter in the museum and the exact kilogram in the museum, and there's the one atom of what, plutonium 24, 124, whatever, and they're checking off the decay life, half life.
Yeah, well, okay. See, that's the thing. But it's based on real things. Okay, so here's where this comes from. Now, the meter. We're not going to address all of these items. We're going to talk about length, time, temperature, and mass because those are the things that, well, they matter to me most. Right? I don't worry a whole lot about quantity. I can't count to a mole. Okay.
We'd be here a very long time if you did.
This is a long episode. Zach's going to kill us. We're going to start counting to a mole. All right. And I don't do a lot of stuff with current and luminous intensity, but we're going to talk about length, time, temperature, and mass. Okay. So the meter was originally defined. Right. This is the French guys, right? Okay. This is French Revolution. This is the pinnacle of the rationalists and this idea that we are now enlightened. We can throw off, Harry, we're going to throw off all the ancients and we're going to stand new in this grand world that we're, right? Okay. So the meter is 1/10 millionth of the distance from the equator to the North Pole. That's what it was.
And I'm sure they had somebody out there with one of those little wheel things, and they were just rolling it, uphill, right, to the North Pole.
Yes, right. So, and the thing was that, you have to measure it along what they called a great circle, which is one of the meridians. Okay, and we're going to do one of these one day when I find the book for the reference, probably after we move into the new house. But the idea is like, the French thought they didn't think. They knew the prime meridian must go through where, Harry?
What, through Paris?
Through Paris. Where, you know what?
Where else could it go?
Where else would you put it, right? And in fact, if you go to the, what's it called? The Museum of Justice or Science or whatever, that you go to the observatory there in Paris, and there's a line on the floor, and it says, this is the meridian. Here it is. And that was the place where they would measure this thing. Okay, so, but if you do that, if you start marching from the equator along the prime meridian to the North Pole, you're going to hit some water, right? That's a problem. Okay, mm-hmm. And we have found out later that the Earth is not a sphere; it's kind of a squashed ellipse. It's a beach ball. You squish at the top and the bottom because it gets kind of stretched out because it's spinning. Okay, so the meter is 1/10 millionth. Okay, so but I'm going to give them credit for this. That's a great idea. A meter,
well, 1/10 millionth. Makes sense. Yeah. They know it's a really long distance, and we'll divide it up by another power of 10.
Yeah, otherwise you'd have to work with 10 million meters. That would be, let me see if I get this right. 10 million meters would be 10 megameters.
Yeah.
Yeah, okay, so there you go. Okay, so, and then you can get a milliliter. You can get volume from distance, right? Because you take if you take a cubic centimeter, you take a centimeter by centimeter by centimeter, it makes a little cube about the size of a small die.
Mm-hmm.
All right, that's a milliliter. And you take 1,000 milliliters, you get a liter, and it turns out a gram is the mass of 1 milliliter of water right above freezing, right?
Okay.
So then 1,000 milliliters is 1,000 grams, which is a kilogram, right? And you're like, okay, this
all works out.
This is it, and you know what? That's a great thing. Anybody can do it. You don't need you don't need to chop off the king's thumb and carry it around the realm, right? So, and that's a grand and wonderful thing. And then seconds are a little difficult. When I was reading, I was at your house babysitting here. I need to tell you this. And when we were babysitting for you guys, I was sitting there watching. I was watching your daughter play with some little toy, and I was thinking about how I wanted to tell her that things that have really long pendulums swing slower than things that have short pendulums. And I thought about Galileo watching the lantern swing in the church, and I thought, well, the second ought to be defined relative to a pendulum of like 1 meter. I mean, that was my thought.
Stick them all together.
Yeah. So then you was like there. So then you get second. And in fact, when I started, and of course, then I was sitting there babysitting. I was babysitting, and I was watching your daughter, and meanwhile I was scrolling on my phone,
looking at Newtonian physics. Sure.
Well, I was just, how did they define the second back in the old days? And it turns out that was one of the plans. Was the second should be that. And if you go look up the pendulum equation, you can see where when you plug the numbers in, if you have a pendulum that's length about a meter, it should take about a second. I forget if it's a second one way across or if it's a second across and back. I forget.
Like what, with a weight of 1 kilogram at the bottom?
Well, it just doesn't matter, right?
Oh,
The
yeah.
weight doesn't matter, right? But what does matter, okay, and this is where they got into trouble. The question is, where do you measure that? Because the gravitational constant G is not the same everywhere on the planet. All right, so
Sure, and we can go into that in a different episode. But
okay, so
we'll stick with your 4 main points here of SI units.
Yeah. So I got what? Do I have to stand at the cathedral in Paris, at the altar, or do I stand in the observatory? Do I stand at the equator, at north? Where do I? Okay, so that's the thing. So I thought it'd be kind of cool if they did that, but they didn't define it that way. They originally defined the second to be 1/86,400th of a day. Now, 86,400 comes from 24 times 60 times 60, which to me is really interesting because I think if you wanted to go super metric, you would say, I'm scrapping
10.
I'm going to go right. I'm going to put 10 hours in a day. I'm going to put 10 minutes in an hour, and I'll put 10 seconds in a minute.
Sure.
And actually, the French did that. Okay, back at the beginning of the French Revolution, for about 15 years, from 1792 to about 1806, Napoleon got rid of this idea. Bad idea. He said, no, we're not going to do that. But the French said, we're going to put 10 hours in a day. We're going to put 100 minutes in each hour. And we're going to put 100 seconds in each minute. And therefore, if you do that and you use 2 digits, you can write the time out and you don't have to do a fraction. Like 45 seconds is 3/4 of a minute. You don't have to do that. And all the math works out. But you know what? That didn't really catch on. And one book I read on this, Harry, said that you can get people to converge on like standardize. You can get people to standardize when it matters to them economically. Right? So if you were trading me a bushel of apples for a chicken or something like that, I need to know what the standard unit is so neither of us get screwed. But we don't trade time very much, at least not minutes in a day, right? We may trade our work hours for something, but so there's very little desire to standardize that time, and that 24/60/60 thing has been around since the Sumerians or something like that. So that never went very far. Okay,
but we still don't have the definition of a second yet.
Yeah. Okay. Well, we're going to get to a second here. All right. So I'm going to go back to temperature though, because temperature is one that I talk to my friends in Canada, and they'll say it's so hot up here. It's 34, and I'll be like 34.
You're constantly thinking.
Yeah, I was like,
what's even worse about that? They'll say 34 is really, really hot, but 30 is okay.
Yeah, well, but their degrees are bigger.
They're 2 point something, right? More.
Almost
2.
Yeah, 9/5 of one of our degrees. So it's like 4 degrees for them is like almost 10 for us. So yeah, that is a big deal going from 34 down to 30. So okay, so where does this come from? Okay, my Canadian friends use degrees Celsius. And Celsius is awesome. It is a wonderful thing. When I first learned it, I was like, why do we even think about using Fahrenheit? But Celsius goes from 0 freezing to boiling at 100, and you put 100 graduations in there equally spaced. Done. I mean, what else would you do? It's easy peasy, lemon squeezy. Right?
It's great. It only measures water, but continue.
Yeah. You can take the thermometer out of the bath there, Harry. You can put it in the oven. All right. So okay. So what Fahrenheit did, and he did this. Like Celsius did his stuff in 1742. Okay. All of this stuff is this Enlightenment kind of rationalism thing going on. He did stuff Fahrenheit was 1724. Okay, so he was 16 years prior he was doing this. And you can't blame Celsius for being late to the game. It wasn't like he couldn't get himself born earlier.
Right, it's not like he could read what Fahrenheit did on the internet.
No. But he could read the papers. They started publishing the papers back then. All right, so here's what Fahrenheit did. He said, you know what? 0 ought to be a number that's like so cold that I can't get colder. Okay? Yeah. And he was a lab guy, and he took water and ice and made brine. Okay, which is like, and what that does is it lowers the temperature, right? It draws the energy out. Okay, lowers the temperature, and that's how you make ice cream. In the old days, we used to make ice cream, and you'd put salt and ice outside of the thing, and then that would freeze the ice cream and then
As you churn, yeah.
and you would churn it. Okay, so he put 0 there for he made the coldest thing he could make in the lab, essentially. And then he said human temp. Now I've read 2 things on this. I read one where he said he made human temperatures to be 100 degrees,
Okay.
and I read one where he made it to be 96 degrees. Okay, and he noted that if he assigned standard body temp to be 96 degrees, then water would freeze at 32. And going from 0 to 32 to 96, those are nice powers of 2, Harry.
Mm-hmm.
32 to 96 is 64 degrees. And you can divide that in half 6 times and get nice little graduations. So halfway between 36 and between 32 and 96 is 64. And you can divide that in half. And so you get a lot of... So he was like living in this binary split world where Celsius was living over here in the space 10 world. And, I can't... Now, he didn't measure the temperature quite right. Okay, he had it at 98.6. There's been some conversions and adjustments since then, and it landed at 98.6, which is kind of a weird thing to be.
Which is still... I'm sure we can read about some other things, but I've also read that, I forget who was doing it for standard body temperature, but when patients would come in and the doctors would take the temperature, and they were starting to standardize what is standard, all of them were on the higher side because the patients that were coming in were sick and febrile.
Yeah, that's
right. So standard temperature, if you go and take your temperature, I'll bet you it's lower than 98.6. Mm. If I take mine on a regular basis, it's usually closer to 97.7 or 97.8.
Yeah, mine is low as well. I'm in the 96s, low 97s typically.
Yep.
That I guess that comes from a heart that doesn't beat, right? I mean, that's... So, all right, so this, but, okay, so Celsius had an idea, which was very good. Fahrenheit had another good idea, okay? Now, it doesn't quite line up with this idea that Fahrenheit was kind of human-based, right?
Mm-hmm.
Right? And then he liked powers of 2, and Celsius was kind of powers of 10 based, and he liked to base it on more universal earthy stuff, right? They're both pretty good ideas. I like Celsius better from a practical point of view, but still in my head, I spent 57 years doing things in Fahrenheit.
Yeah.
And I mean, asking people to change is real hard. And certainly when it doesn't matter to them economically, they're less likely to standardize. Mm-hmm. So anyway, so that's the temperature thing, okay?
Don't get too many ideas, because otherwise we're going to be taxed for using Fahrenheit. Yeah,
don't get me... Okay, that will not be one of the episodes. All right. Okay, so those were the ideas for the metric system. But it turns out that those great ideas, although they were great, they didn't get implemented that way. Okay? The meter has had 5 unique definitions since it was first conceived. This blew me away. Okay? When it was first defined in 1790, I wrote 3 here. I wonder if that's true. 1793, the meter was 1/10,000th of the distance from the equator to the North Pole. Okay?
Yep.
Right. 1799, 6 years later, they were like, yeah, we're trying to, we don't really know.
The tape measure wasn't long enough, and we had to swim across the ocean.
Well, they actually did. You know how to do surveying?
Yeah.
They were surveying that. They had the guys with the chains out there dragging them up the hills, going over. They were trying to do that.
Mm-hmm.
Okay, so that was so after in 1799 they came up with the idea of the prototype bar. There was a piece of metal in the archives at the National Observatory, and that was the meter. Okay, now you can't complain to me that the foot or the mile or the gallon, that those are arbitrary, and then defend the metric system as being not arbitrary.
Especially when it's been updated since 1793.
Oh, yeah, wait, so that was in 1793 they started. 1799 they switched to the bar, okay? In 1960, so they went 161 years with the prototype bar. And I guess there were other bars, because we have one in the United States. We had one. It sits at NIST, I think. Okay. And the French have the meter, and we have like the meter, like we have like the off-brand. Okay. We have the Megablocks meter to the Lego meter.
There you go. Yep.
Yeah. Okay. So in 1960, they defined the meter relative to a number of wavelengths of one of the peaks of the oscillation spectrum thing of Krypton 86. Okay.
Well, I'll be right back. I'm going to grab my Krypton 86, Adam. That stored my tape back here.
Yeah. So and you got tape measures. You can measure that, right? You can lay it out. Okay. So there's
I've got the copy of the off-brand bar.
You lay it's the same length. Okay. And then in 1983, they defined it as 299,792,485th of that. Take that amount of time in a second, okay, and measure how far light travels in a vacuum in that period of time, and that's going to be the meter.
Oh, so I can get rid of my Krypton atom, and I just turn on a flashlight really fast.
and hold up your little stick and measure that, okay? So okay, so that's the reciprocal of the speed of light. I was like, well, okay, I got it, and that's constant. Speed of light is constant everywhere. Yes, probably in a vacuum. Yes, it is. Okay, so that is the assumption, right? Right? So it is. That's the speed of light in a vacuum. And then in 2022, they defined it, Terry. In the last, we're in July.
Last couple months, yeah.
In the last couple months, they've defined it. My bet is that they put it some fraction there at the end of the speed of light. They probably have refined that length or that time it takes, right? So they're not really. They say they're measuring it relative to the speed of light, but they're really measuring the speed of light relative to the meter, right?
Yeah, sure.
But anyway, so that's how it's defined. So it is completely arbitrary. It is 100% arbitrary, but it's based on something that we're pretty sure is never changing. Not like the king's thumb, right? So that's, I guess.
Measured at age 12 and measured at age 26.
Measured at age 300 now that he's dead and is sitting there in the vault. Okay, so where do these? Okay, that's where the meter comes from. All right, and these other things come from similar kinds of things. I mean, if you read where these things come from, I had it here. Here, okay. The second is not defined in Torah the pendulum like we would do. It's defined by taking the fixed numerical value of the cesium frequency of the unperturbed ground state hyperfine transition frequency of the cesium-133 atom. Well, you got one of those lying around, don't you?
Oh, it's my other safe.
All right. So that frequency is 9,192,631,770 hertz. So you count that many of those little things, and however long it takes you to count that many of them, that was 1 second.
Well, that's good.
Yeah.
Can you count that fast?
But it's not arbitrary. All right, and it's arbitrary. And the speed of light is defined relative to the meters from the speed of light. The kilogram is defined by taking the fixed numerical value of Planck's constant to be 6.626070015 times 10 to the minus 34th when expressed in joule seconds, which is equal to kilogram meter squares per second, where the meter and the second are defined as above. So
you get all these things in a room, along with a priest and a rabbi, and I'm sure we can figure out all the rules to the universe.
All right, so pretty much you start with how long it takes the cesium atom to bounce that many times, and then you just you figure out all these other ones. As long as you can watch light go a meter, or like you can count 300 millionth of a second. It's like, okay, these are all completely arbitrary. They're based on physical constants. I got it. But they are completely arbitrary. Let's not pretend that it is some sort of grand, perfect universe thing. Okay, so that's what. So where'd the inch come from? That's a question.
Well, I'm here to get learned, right?
Yeah, well, you get learned. Okay, so an inch is 1/12 of a foot. Okay, and so you're like, well, why did 12? Well, 12 is a really great number. I mean, 12 is a wonderful number. You can divide 12 by 6, you can divide it by 4, you can divide it by 3, you can divide it by 2. And if you don't live in a metric world, okay, and peasants in the 700s didn't live in a metric world, they lived in a fractional world. Everything was fractions for a long time. I mean, I like decimals better, Harry, but people did fractions, and they did them a lot.
Fractions are rational.
Yes, by definition. All right, so All right. So and then the foot comes out of like the Roman mile. Okay. So you have the Roman soldiers, boom, 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 boom. They're walking along. All right. And they would go 5,000 Roman feet. Right. And a Roman foot was pretty much 1/5 of a two-step of a two-step pace.
Okay.
Okay.
Yep.
So and I always think about 3 feet to a pace, but when I'm pacing things off, I'm pacing them off very deliberately, like I'm measuring like course yardage on a golf course, or like I'm in a big room. I'm trying to figure out how wide it is. I'll take steps and divide by 3, but I make very deliberate steps. I don't. I guess when you're marching, you've marched.
Yeah.
You're not stretching your step out. You're marching together, right? And the Romans, when they would march along, they would drop a stake every 1,000 paces, and that would mark off the mile. So if you were well fed and well rested, your miles would be a little bit longer, and if you were lollygagging, then your miles would be a little bit shorter. But that comes. I mean, these are really really old measurements. Okay, and in the time since then, since the meter came along, all of these things are now defined relative to the meter. So you can say, how big is an inch? How big is a foot? Well, you can almost go back to the metric system and to the light bouncing around or the cesium atom bouncing back and forth, right? Gallons. How many quarts in a gallon, Harry?
4.
4. It's a quart, right? It's a quarter, right? So, right, and there's 2 pints in a quart, which is 16 ounces, which is 2 to the 4th, right? There's 8 ounces in a cup, right, which is 2 times 2 times 2. I mean, so there's a lot of powers of 2 in the volume measurements in the imperial system.
Mm-hmm.
Right? So tens are hard. Cutting things in half, if you're a baker or if you are, if you're working like measuring out, I don't know, grain for your horses to feed them, it's measuring in tenths is hard. Measuring in halves and quarters is a lot easier. So that's where these things come from. That's why I have the imperial system. Okay, so mass in the metric system is in kilograms. Okay, and notice the fundamental unit isn't the gram, it's the kilogram.
Right.
Well, why isn't it the gram?
You tell me.
Well, that's what I think. So it should be the kilogram. So it was like a millikilogram is a gram. So should I be using kilograms or should I be using right? Okay, so that's just the thing. Now, mass is not weight.
That's right.
Weight is a force. Mass is the resistance to motion. And it's interesting if you go back into the Middle Ages and stuff when they were figuring out what mass was and how it was different from weight. The physics problems we always look at now are like, all right, Johnny has a mass of 2 kilograms, and he applies a force of 3 newtons. What's the acceleration of the mass? That's what we ask now.
Yep.
But what they did back then, they knew the force and the acceleration. They always tried to find the mass. How massive is this thing? Was always the question. All right. So the idea was like I push it. Like if I push the same two different things with the same force, I can see how massive they are by how fast the thing accelerates. Right. Yeah. And that's how they looked at the problem. Okay. So force is in newtons in the metric system. It's in pounds in the imperial system. But people use pounds as mass anyway. They still do.
They use kilograms for weight anyway.
Do you know the imperial unit for mass?
Couldn't tell you.
It's a slug.
Okay.
It's called a slug. Yeah, that's what it is.
I did know that.
Okay, so all right, so I'm going to get to one final thing on this. All right, but the meter has had 5 definitions over the past 225 years. That's more than one every 50 years. Okay? These other ones, the foot and the inch and the ounce and the gallon, it's like, yeah, there are all sorts of different ones, but they came from all over, and they've been around for what's after centuries.
Millennia?
For millennia. They've been along for multiple kilo years. All right, so, give them a break. Okay, so, but why does the U.S. refuse to change? Okay, that's the question. Certainly when it comes to distance, why do they refuse to change? And my answer is the Land Ordinance of 1785. Right, the Land Ordinance of 1785 worked with how do we divide up the Northwest Territory, which is the area north of the Ohio River and west of Pennsylvania, that the area we call the Midwest now. Okay, yep. So the area Ohio, Indiana, Illinois, Wisconsin, Iowa, Minnesota, that stuff. How do we partition that out so that when settlers go, we can have an organized way of doing this, right? And the ordinance called for the construction of townships. Okay, so you draw a line and you draw another line 6 miles out. Okay, and then you go vertically 6 miles. So you're going to have a square that's 6 miles on each side because it was 1785 and there was no what? There was no metric system. All right, so they went 6 miles up and 6 miles over, and you have a square now that is 36 square miles in area. And they said this is a township. It's a little group. All right, and each township is going to be divided into 36 single square mile plots, right? And they were all numbered. They were little plots. It was like, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 30, all the way up to 36. And the rule said that 4 of those plots were going to be held by the federal government. One of those plots was going to be reserved for the school that would be placed in that township, okay? And then the rest of these little 1 square mile pieces, which were exactly 640 acres, that these things were going to be, they're going to be bought up by people and then sold off and developed. They were going to be subdivided. Okay, so if you have a square mile, if you have a township that is 36 square miles, and each square mile has 640 acres, then that means that there are 64 little 1/8 of a mile by 1/8 of a mile patches in there. Right, and each one of those is 10 acres. Okay, and they would divide these things down into 10-acre sites. And anybody who knows anything about farming knows that there's, you'll have the back 40. You would buy up a chunk of maybe 80 acres or 40 acres, right? That would be the piece that you get. And if you're going to have access to all these little townships, Harry, where are you going to put the roads? Are you going to put the roads right through the middle of the township? Or are you going to put it along where, Harry?
Put it around the edges.
Put it around the edges. Okay, so they built these roads, these straight east-west, straight north-south roads. There's a little bit of issue when you get higher latitudes. The Earth kind of curves, and spherical geometry is not the same as planar geometry. But they're these roads. Okay, the roads exist in the heartland of America. The roads exist at a grid of 1 square mile. Okay, and they were laid down that way in the late 1700s before there was any metric system. Okay, and everything about it is based on miles, right? And then the other thing that's kind of fortunate, we have cars now, Harry, and you drive at a nice high speed in a car, it's like 60 miles an hour. And if I drive,
pretty quick.
It's pretty fast when you're used to riding a horse.
Yep.
Right? So if I'm going 60 miles an hour for 1 minute, how far do I go?
Oh, probably exactly 1 mile.
1 mile. Click, 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 click. All right, so those people who say, we should convert to the metric system, are like, hey, I'm all for it. Right? But one thing you're not going to be able to do is re-grid the heartland. You can't do it. What are you going to do? Move the roads? Put them on a 1 meter grid or 1 kilometer grid? A megameter? What are you going to do? How are you going to do that? And you can't put them at 1.6. Who does math with 1.6? Nobody does, right? So why doesn't America change? That's why. It's the Land Ordinance of 1785. And don't say, well, they could have used the meter, because they couldn't, because it wasn't around. Okay, so I don't know. That's when people say, why don't you change? Because it works, all right? All my grandma's recipes, Harry, they're all written with cups and ounces and gallons and quarts and tables. That's how they're written, right? They weren't written in milliliters. And granted, I like it. It's a lot easier to divide by 10 than it is to divide by 12. But you know what? It works, right? And unless it becomes economically viable to switch, they aren't going to switch. It's all good.
Oh, we all know how hard it is to double or triple or half a recipe. It calls for 2/3 cups. No one likes doing that. No one measures anything in 2/3 cups.
Well, it is. But but if you have these measurements, if the thing calls for 3 cups, right, and you got to convert that to metric. Okay, so and then what does it make, Harry? It makes a dozen cookies.
Yep.
Right? It makes a batch of 2 dozen cookies.
Well, it's because a tray of a 3x4 is really easy and fits in the oven.
And fits right.
I'm just going to put in a 2x5 tray.
We're going to make it 2. Well, good point. All right, and that's the problem with 10. That's the only problem with 10. 10 comes from I have 2 hands and each have 5. It'd be better if I had 3 hands, each with 4 fingers. Then I would have 12.
I have 3 arms.
All right, yeah, it's like, but you know what? I don't have that. When I build rectangles and pie plates and things like that, 12s are a lot nicer. Do you ever try to cut a pie into 10 pieces?
Oh, it's rough.
Yeah, it's rough. You break out in hives doing that kind of thing. So, anyway, Harry, that's where we are. That's the answer to the question. When you fly over the great Midwest and you look down and you see all those little squares, you know that those are at a mile. And if you know that, you can estimate the speed of the plane, Harry, by watching how many of those the wing. If you're like a seat by the wing, you can check how many of them tick off in a minute.
Yep.
You can calculate your speed. Anyway, that's where you got it.
Probably going to come out to about 600,
Yeah, well,
which is also nice.
yeah. So, yeah, I went 600 miles an hour. Well, I don't think. What is Mach 1?
800 something.
Is it that high? Okay. So you can go pretty fast in a plane. And that's why America doesn't switch. If you got a better idea, let us know. We'll entertain that. Harry, you got anything else?
I don't think so. Some good time.
All right. Well, that's what I think. That's how it goes. Just remember, whether you're using metric or whether you're using Imperial or whether you're measuring it in ZAC units, I don't even know what those are. But no matter how you're doing it, remember to seek the good, be the good, and spread the good. Enjoy the adventure of life.